A pleasant day to each and everyone. This is Arnold Idria BULFA, and today I'll be discussing one of the topics of Math 204. Sampling distributions. Sampling distributions is formed when random samples of size n is repeatedly taken from a population. By the way, what is sampling itself? Sampling refers to the strategy used by a researcher to pick a subgroup from a larger group, then use this subgroup to make judgment for a larger group. Then sampling distributions is the probability distribution of a statistic. A statistic such as the sample mean and sample standard deviation is computed from a sample. Since a sample is random, a statistic is a random variable. It varies from sample to sample in a way that cannot be predicted with certainty. As a random variable, it has a mean, standard deviation, and a probability distribution. This is the illustration of the population and the sample mean. By the way, population refers to all the members of a specific group, then the sample consists of all the elements considered in the study. As you can see on the illustration, the sample mean or the sample's size cannot exceed with the size of the population. In solving a particular problem involving sampling distributions in probability, you must consider the properties of the sampling distributions of sample means. First, the mean of the sample means, represented as mu sub x bar, is equal to the population mean, represented as the mu. So it means that the mean of the sample means is equal to the population mean. Second property is the standard deviation of the sample means, represented as sigma sub x bar, is equal to the population standard deviation sigma divided by the square root of the sample size n. The sample standard deviation is also called as the standard error of the mean. It can be solved through using the equation sigma sub x bar is equal to sigma over the square root of n. It is noted that if the sample size n is large enough, the sampling distribution are normal or nearly normal. For this reason, the sampling method is called as the large sampling method. When n is less than 30, the sample is called small. Next is the central limit theorem. The central limit theorem is one of the most important theorem in the practice of statistics. It allows us to make hypotheses about the population. Furthermore, it tells us that the sampling distribution of the mean of any independent random variable are nearly normal or normal if the sample size are large enough. First, if the sample size n is greater than or equal to 30, are drawn from any population with the mean mu and the standard deviation of sigma, then the sampling distribution of the sample means approximates a normal distributions. The central limit theorem says that no matter what the distribution of the population is, as long as that the sample is large, meaning of size 30 or more, the sample mean is approximately normally distributed. Next property of the central limit theorem says that if the population itself is normally distributed, the sampling distribution of the sample means is normally distribution for any sample size n. Meaning, if the population is normal to begin with, then the sample mean is a normal distribution regardless of the size. The equations used in the central limit theorem. First, mean of the sample means. So mean of the sample means is represented by the equation mu sub x bar is equal to mu. Second, the variance of the sample means is represented as sigma squared sub x bar is equal to sigma squared over n. Then, the standard error of the mean or the sample standard deviation is represented by the equation sigma sub x bar is equal to sigma divided by square root of n. Probability and the central limit theorem. To transform a sample x value to a z-score, we'll use the equation value minus mean over the standard error. Then it is represented by x bar minus mu sub x bar divided by sigma sub x bar. Since population mean is equal to the mean of the sample means, so we have x bar minus mu divided by the sigma over the square root of n. So in simplified form, z equals x bar minus mu divided by sigma divided by square root of n. So first, we will solve first the population mean. So in solving the population mean, we just simply add the following data and divide it by the numbers of population, which is 5. So 2 plus 3 plus 6 plus 8 plus 11 is 30 divided by 5. So our population mean is equal to 6.0. We will solve for the population standard deviation. So before we can get the population standard deviation, we must first solve for the population variance. So in solving the population variance, we must only subtract the population mean from the member of the population represented as x. So the member of the population are 2, 3, 6, 8, and 11. Then we must pair the difference between the population minus the mean. So we got 16, 9, 0, 4, and 25. So in getting the variance represented as sigma squared is equal to the summation of the square of the difference between the x and the mean times the probability of x. So we got 10.8. So now, get the square root of the variance is equal to 3.29. So 3.29 is our population standard deviation. Now, we will now solve for the mean of the sample means. And remember that we have the sides 2 and we have replacements. So, our sample will be 2 and 2, 2 and 3, so on and so forth. So, with a total of 25. Then, in getting the sample means, we only get the sum of the two samples divided by 2. So, following the same procedures to all the samples, so we have the sample means of 2.0, so on and so forth. Then, we must verify that this mean of the sample means is equal to the mean of the population as one properties of the sampling distribution. So, the mean of the sample means represented as mu sub x bar is equal to the summation of the sample means divided by the number of the sample means. So 150 divided by 25 is equal to 6.0. So now we have verified that the mean of the sample means is equal to the population mean. The standard error of the mean, so we have the equation sigma sub x bar is equal to the population standard deviation over the square root of, and our standard error is approximately equal to 2.33. In solving this problem, we must consider the properties of the sampling distributions, that the population mean is equal to the mean of the sample means. Then we have population mean is equal to the sample mean, so our population mean is 2.61. Then our sample size is 100. Then remember also the equation in solving for the standard error of the mean, which is the standard error of the mean is equal to the population mean divided by the square root of the sample size. So our population mean is 0.5, then our sample size is 100. So 0.5 divided by the square root of 100 is equal to 0.05. Then remember, we must get the probability of x is less than 2.71. So in transforming a particular x value to a z-score, we must use the equation z equals the sample minus mu over the standard error of the mean. 2.71 minus 2.61 divided by the standard error of the mean, which is 0.05. That's yield our z-score to 2. Then using the standard normal table, so we can get the cumulative area of the z-score less than 2. So probability of x less than 2.71 is equal to the probability of the z-score less than 2. Then its corresponding cumulative area is 0.9972. That's the end of our discussion for the sampling distributions. See you on the next presentation.